Hello, welcome. It's time for chemistry. How's everyone's weekend? What did you do, Ellie? You already dyed your hair. Did you spill your coffee this morning? Everybody's waiting in suspense, Ellie. We want to know what you did. I pierced my own ears my seconds. So you gave yourself your second ear piercing? Did you do like the ones like up here, or did you just do like a second down here? Yeah, no. I mean, I gotta know the details, right? Gotta know what to expect. Oh, okay. I got you, Ellie. I gotcha. I gotcha. Some people do like the I don't know what this part of your ear is called, like the this part right here, and they pierce that part. I can't remember what that's called. My anxiety levels are yup too, Trinity. Yup. No, it shouldn't be that bad, Trinity. If you've been keeping up with the homework, um, it's gonna be yeah. I've actually heard that one too, Trinity. Um, I I heard the test. Like I said, it's not gonna be like a usual test that we have in my class. It'll probably be like half the length of a normal test. It shouldn't be too bad. So, uh, maybe Simon. There's some weird people in the world. There's some weird people in the world. You could have started the homework that's due Thursday, Zach, if you wanted to. A couple of people were catching up on the last week's homework because they missed it. But you could have started the assignment that's due Thursday. If you didn't, it's not a big deal. After today, though, for sure, you can work on that over the next couple days. Monday mornings. Anybody do anything fun besides Ellie piercing her ear by herself, which is impressive. I'm trying to think what I did over the weekend. Probably nothing. Yeah, most people are like, nothing. Stayed home. Dirt biking, that's fun, Jake. Taking dogs on a walk. We went on a walk. Oh, we took our kids' bikes, and went running. Shooting's fun. What did you shoot, Hunter? Just shotguns? Gardening, that's a good pass. Ooh, rifles, that's fun. Yeah, rifles are fun. Get some long range targets. So Luke, I am still going to be having class on Friday. Um, trampoline, Drake. Gotta say trampoline. But anyway, so Luke, to answer your question, um, I'm still going to be streaming on Friday, even though it's technically like a comp day. Um, but but that's just because we have the test coming up. So it's not an official holiday. I'm still going to be streaming. If you can't catch the stream because you're doing something, you can just watch the video on YouTube, and you should be fine. So yeah, I'm still going to be streaming. Yep. Yep. I think the only day I'm taking off is Memorial Day, really. Um, but yeah, I've got to start. They told us last week that we need to the parts of the building that are getting demolished over the summer. We need to move stuff out, and my classroom is in that part of the building that's getting demolished. So I'm going to be moving stuff on Tuesdays and Thursdays in the mornings. So I'm going to be going to the school and getting stuff moved. Ugh. Yeah, ugh. Big ugh. I could potentially bring home some chemicals, Sadie, and we could I could maybe do some things from here. So the last day of school, Lauren, is like the end of May. I can't remember exactly. Yeah, but it's not like, it doesn't really go that far because graduation is May 27th, technically. It's like we do every year at the end of the school year where the last couple of days aren't really real days. I'm going to be working all the way up until, I'm going to put out a calendar for next month later this week. I'm going to be working all the way up until May 25th is going to be the last day for us. Yeah, you're good, Sandy. Oh yeah, so if you have stuff in your gym lockers, make sure you get those stuff cleared out if you care about any of it. Otherwise, it's getting garbaged or donated. Thanks, Mr. Weaver. No, Drake, the diatomic elements are not diatomic when they're ions. They can be single elements as ions. Is it really 6 months, Lauren? I didn't think it was that much. That's crazy. Oh, yeah. Well, because but really we only go to school 9 months, so we're missing 3 months-ish of school, and so yeah, it'll be half and half. Huh, that's interesting. I think there's some sort of a protocol. It's what, like 11 to 1. You got an email about it. Yeah, there's a schedule in the email that got sent. So, Ellie, maybe if you're not a senior, right, you still have all your people. We could do like a yearbook signing day the first week of school, which would be kind of fun. 2 meters. We were just say 6 feet. We're still in America. We still use the metro or the imperial system. F in the chat. I think that. Anyway, we'll block that. 2 yards. You could say 2 yards. That'd be fine. All right, let's get started. 200 centimeters, indeed. Yes, that's the high class, big brain. You can say European scum, that's fine with me. All right. Okay. So let's get into decomposition reactions. Rest of the word scum. Yeah, you guys can say scum. I don't know why it doesn't like the word scum. All right, decomposition reactions. So we've already talked about decomposition reactions as having the general format of some compound, AB, breaks down into A plus B. So I wanted to give you a little more, like a little more specific example of what you might see for that. Okay, so what we can think about is we can think an actual example, something like sodium chloride. If you take sodium chloride, you actually have to get it hot enough to where it's a liquid, and then you run electricity through it. Right. You can actually get sodium chloride to break down. Muffins. My kids love muffins. All right, so sodium chloride as a liquid, that's an L. Sodium chloride as a liquid, if you add electricity through it, you can get it to break down. And so what would it produce? What's the only things that sodium chloride can break down into? Yeah, sodium and chlorine, but you got to be careful. These are elements, so they're going to break down into their elements. So this is sodium solid and chlorine gas, and we know that chlorine is diatomic, and so it is going to be Cl2, right? So we're going to get sodium solid and chlorine gas, okay? So we want to make sure we balance the equation, okay? So we need a 2 here and a 2 there. Right, that would balance it. So 2 sodium chlorides as a liquid plus electricity is going to make 2 sodium solids and chlorine gas. Okay, good, right? Now we can do this with any sort of chemical. Any sort of chemical, you can heat up any ionic compound, I should say. You can heat up, add electricity through it. It'll break down into its elements, right? How do I know what? Trying to do the balancing? So let's see. So they are not ionic because they have the same charges as before. Well, they're elements. Their charges go to 0. So here the sodium's a +1 and the chlorine's a -1. But when you actually break it down using a decomposition reaction, we're not splitting it like we would be dissolving it. We're actually breaking it into its elements. We're breaking these ionic bonds, and we're restoring the electrons. We're making the sodium go back to being neutral, and we're making the chlorine going back to being neutral. So we're forcing this to happen. The longest chemical equation, Drake? I don't know off the top of my head. There's some crazy ones. Let's see, the equation, all the way you're just like boom, boom. Oh. That's just because I've been doing it for 10 years. I probably should have done it faster. Sorry, the octocore bear, man. This is because of COVID-19. I wish I could have been your chemistry teacher. I love teaching chemistry. Makes me sad when people say they hated their high school chemistry teachers, because I feel like that's sad for science. Okay, so they get put in their natural state when they split up. Yes, Cooper, they get split apart into their natural state when they split up. Okay, let's do another example because you guys are a little struggles with this. Let's take something like, I don't know. Let's do let's do something a little like really crazy reactive. So we'll do nitrogen trifluoride, right? And if you just heat this compound up, it'll break down. Okay. So let's see. Hold on. Yes, is chlorine? To answer your question, Lauren, the Cl2 is because of Honeyfickelbear, right? Our diatomic elements. Ellie, why do you want me to say live, laugh, love? I'm not that basic. Oh, good old Igor. Yeah. Okay. So here we go. So what's nitrogen trifluoride going to break down to once we heat it up? Oh, so there's 3 fluorines in the compound because in this case the nitrogen is actually forming a positive 3-ish. It's a molecule, but it's a little tricky. You guys won't have to worry about that, Zach. I'm always going to give you the reactants. I'm just going to ask you to produce or predict what's going to be produced by the reaction. And so if you have a single compound and you add either heat or electricity through it, that should kind of be a sign in your brain to say, oh, okay, this is going to be a decomposition. I need to break it down. Endothermic, Jonathan. Endothermic, because we're adding heat. Yeah, so Icy Snow's got it. It's going to be, we have to have nitrogen, right, N2 gas, and F2 gas. So we're going to make nitrogen and fluorine gas. Now, the reason I know both nitrogen and fluorine gas, just to remind you, if we look on a periodic table, okay, the, you see how nitrogen and oxygen and fluorine are all in red text? The reason they're all in red text is because they are gases, right? Same with helium, neon, argon, krypton, xenon, radon, right? The noble gases, they're all gases. Bromine, which is, you know, up here in blue, is a liquid, and mercury, right, is a liquid, okay? But all the other elements are all going to be solids in their standard states. So most things are solids, right? 2 things are liquid, mercury and bromine, and everything else is a gas. The noble gases are gases. I know, it's crazy. Okay. To answer your question, Octocorbear, the reason why is we can start to predict, say we have like, we're going to get into this next week as a class, but if we start to predict like we have, 20 grams of sodium chloride, we could predict how much sodium and chlorine we're going to produce, and we need this balanced chemical equation to let us predict that and to do the math for it. So that's kind of what their purpose is, what their point is to be able to do some calculations and some math. No, I'm not modding you, Fallon. Yeah, and all those temperature values are all those phases are room temperature, Drake. Okay, so all right, we need to balance the equation, of course. We have 2 nitrogens here and only 1 there, so we need a 2 to balance it. And then we have 6 fluorines because they multiply, and so we would have a 3 here to make 6 fluorines. Okay, so our coefficients are, as Cooper's pointing out, 2, 1, 3. Okay. I know you did. You did it before I did. I'll give you the credit. All right, letter B. We're gonna do special cases. All right. So there are 3 special cases that I want you guys to be able to know and recognize. So compounds breaking down to their elements, right? That's pretty straightforward. But there's 3 kinds that I want you to know, and that is, these are metal hydroxides, metal carbonates, and metal bicarbonates. All right, so metal hydroxides, metal carbonates, and metal bicarbonates. These compounds don't break down into their elements. They break down into a specific set of stuff. And so we'll do an example of that. So let's start with a metal hydroxide. So, I don't know, someone give me a metal. What do we got? Give me a metal, give me a metal, give me a metal. Zinc, someone said zinc. Okay, zinc hydroxide. So we know zinc is a positive 2. So if we take zinc hydroxide, it should be ZnOH2 solid. Okay. So if you take zinc hydroxide and you heat it up, right, we add heat. Okay. What happens is, instead of producing like zinc, oxygen, and hydrogen like you might predict, so hydroxide, carbonate, bicarbonate, those are good reminders of what those formulas are, Zach. Thanks. So zinc hydroxide solid plus heat. What happens is your metal hydroxide is going to break down into the metal oxide, and so we're going to get zinc oxide and water. Now, you can make an argument that the water should be a gas or a liquid. I'm just going to write it as a liquid. But if you wrote it as a gas, I wouldn't count off for it. So the big thing is that a metal hydroxide breaks down into the metal oxide and water. Okay. So ZnOH2 breaks down into ZnO and H2O. Why does that happen, Inya? That's a great question. It has to do with the way that the hydroxide is bound to the metal. It turns out that when you heat it up, if you were to then take the zinc oxide and heat it even further, you could eventually get it to break down into zinc and oxygen. This is kind of like an intermediate step in the decomposition of the zinc hydroxide. So you would have to get it like really hot to break down into zinc and oxygen. So what happens is the zinc hydroxide is more stable to break down into zinc oxide and water. And hydroxides and carbonates and bicarbonates are really common on the Earth's surface, which is why I'm having you do these. So the metal oxide is almost always going to be a solid, so you can just do a solid for the metal oxide. And then water, you can say either liquid or gas, it's fine. Because you are heating it up, so the chance it's probably going to be a gas is high, but I'm just going to write it as a liquid here. Oh, thanks for the follow, Octocorvair. I didn't even notice. Okay, so with the hydroxides, the metal will always become an oxide compound. Yeah. It turns out, Tyler, that with all three cases, the metal is going to become an oxide. All right. So let's see. Some of the other suggestions for metals were uranium. I'm going to do tin. Let's do tin for carbonate. Okay, so with the hydroxides, the metal always become an oxide compound. Yeah, put the jet and follow in. No. Okay, so tin for carbonate. So if we look at tin for carbonate, tin is SN. Okay, carbonate, CO3. If the tin is a positive 4, remember carbonate is a negative 2. And so to balance that out, we need 2 of the carbonates. Right? Okay, so that's our correct formula for tin carbonate. Right? SN parentheses CO3 parentheses 2. If we heat it up, okay, we're going to again produce a metal oxide. So it's going to be tin for, the charge stays the same. So it'll be SnO2. Right? Oxygen's a negative 2, tin's a positive 4. So we need 2 of the oxygens to balance with the tin. And then we have our other compound. Now, what do you think is left? Well, carbon dioxide. Right? So it turns out that when you heat up a metal carbonate, you produce the metal oxide and CO2. Okay. So metal carbonate plus heat makes metal oxide and CO2. C2O2 is not a thing. At least it's not a stable thing. It's called ethylene dione. You're right, Ellie. I have not balanced this equation. This one was already balanced, but this one is not balanced. So I think I just need, if I'm not mistaken, I think I just need a 2 here. 110, 110, 6 oxygens, 2 plus 4 makes 6 oxygens, 2 carbons, 2 carbons. So is the metal oxide that comes out like oxidized metal? Yeah. So a lot of metals, when they form oxides, they form white. Or iron oxide is kind of red or rusty. This tin oxide would be, it's either white or gray. I can't remember. But yeah, no, it's not going to be a metal. It's going to be a very like powdery, kind of a white solid for the most part. So you must have either CO2 or an H2O on the products of this equation, like in combustion. Kind of, Enya. It's just that no matter what the metal was here, so say we had used zinc, calcium, sodium, lithium, whatever, you're always going to get that metal with oxygen and water. Drake, colors are pretty tricky to try to predict. That would be something that you just kind of have to learn by experience. Yeah, colors are pretty difficult. If you're making both of these are white though, I think. So if you're making an ionic compound, chances are it's probably going to be white. But who knows? We kind of talked about para and diamagnetism way back in first try, and that can kind of help predict at least if it's going to be white or colored. But the actual color itself is a little tricky. Okay, we got to do our last one. We got to do a metal bicarbonate. So number 4. What do we want to do for this one? Let's do. I guess we'll do one that's kind of tricky to balance. So mercury, sure, we'll do mercury. Let's do mercury bicarbonate, mercury 2 bicarbonate. So HgHCO3 parentheses 2 solid. So remember the bicarbonate ion. Let's see. Let me make sure I missed the question. You guys can do a Minecraft server all you want. Do copper? No. So yeah, sorry. So does it go metal hydroxide then down to the examples? Yeah. So this is the metal hydroxide. This is a metal carbonate, and this is a metal bicarbonate. Okay, so here we again are going to make the metal oxide. So we're again going to get mercury oxide. So again, metal oxide. But with metal bicarbonates, let's see, heat does the same thing, electricity and other problems, right? Yeah. So sometimes you need just heat, sometimes you need just electricity, sometimes you need heat and electricity. You guys won't be asked to predict that. You'll just need to recognize that if you see heat or electricity, it's indicative of a decomposition reaction. It indicates a decomposition. All right, so the thing is, when you have a bicarbonate, you get both water and CO2 as I'm running out of space, right? So with a metal bicarbonate, it breaks down to the metal oxide, water, and the CO2. Okay, so metal hydroxide, metal oxide, and water. Metal carbonate, metal oxide, and CO2. Metal bicarbonate, metal oxide, water, and CO2. Yes, this is like the combo pack, Ellie. Let's see. To make sure the equation's balanced, I've got one mercury. I've got two hydrogens. I have two carbons, though, so I need a 2 in front of the CO2. And then I have 6 oxygens, and I have 1, 2, plus 4 makes 6 oxygens. No, oh shoot, that's a G. It's just not a very well written G. Sorry, Sadie. Yeah, that's a G for gas. These are hot reactions. You're not going to get dry ice. Drake, there are some like web versions of Minecraft that you can get on your Chromebook. But if it's like one of the school's Chromebook, probably not. But if it's your actual like personal Chromebook, yeah, I think so. 1112. Yes, sir, Cooper. Oh, okay. Then yeah, you should be able to get like at least the browser versions of Minecraft to run. I don't know how that works because I haven't ever cared. Okay, so yeah, that's it for decomposition. So what you need to do is you need to be able to recognize these reactions, right? So if you just have kind of any run-of-the-mill chemical, it's going to break down into its elements, right? It's going to everything's always going to break down into these two things, okay? So compound break down into two elements. You need to know these 3 special cases, okay? Metal hydroxides, metal carbonates, metal bicarbonates. The metal hydroxide breaks down to the metal oxide and water. The metal carbonate breaks down into the metal oxide and CO2. And the metal bicarbonate breaks down into the metal oxide, water, and CO2. Okay. What the heck is a chem pickle, Drake? Like a chemical, but a chem pickle. What's the definition of a compound? Yeah, so a compound's anything, Lauren. It's any combination of elements, right? So we have, pure substances is kind of our overall thing. We have elements and compounds. So if something's not an element, it's probably a compound. unless it's a mixture, right? So we have elements, compounds, and mixtures. Okay, so we got to be careful we keep those all straight. Elements are like our elements, compounds are mixtures of elements, and then, well, I guess elements bonded together is a better way to say it. And then mixtures are when you mix things in like a solution or something. Okay, let's do... that's salt, Cooper. Okay, let's look at the canvas. Boop. All right, so if we go to the canvas, okay, this is our lovely canvas homepage. You should all be very familiar with this, okay? We always go to modules, right? Modules is where you want to go to keep up with the class. Modules. Okay, go to modules. Okay, we've already done the intro. We've already done the chapter 10 part 2. Ah, look at this. Chapter 10 part 3. Okay. Yes, technically you're right, Cooper. It usually has vinegar or something else in it. The test is a week from yesterday, Kate. A week from yesterday. So we have one more assignment due on Thursday, and then we're going to have a test due Sunday night. Okay. So you'll have to do the test over the weekend. Scroll up a little. I'm on the canvas. I'll go back to the notes here in a second. Here. Oops, wrong one. This one. Notes. Okay. So, like I said, we have this predicting equations worksheet. Click. Get our lovely PDF. Open. Okay. So, reminder, this worksheet, right, which is due. Zoom out a little bit. There we go. This worksheet, which is due on Thursday night, right? I don't have the submission up for it yet, but I'll be working on that today and tomorrow. So we should have that available tomorrow. It's going to be due on Thursday night. Okay, yeah, I think I got you on that, Seth. You can always go back and watch the YouTube video that I published soon. People say that it don't be like it is, but it do. All right, so reminder, so on the worksheet, right, you're going to be labeling the reactions as if they are synthesis, decomposition, single replacement, double replacement, or combustion, okay? And then on a couple of them, so on the first 3, you don't have to write total and non-ionic equations. So on the first 3, you're just writing the balanced chemical equation. On the 4th one, you are writing a total and net ionic equation, okay? Back to the 5th one, nothing. On the 6th one, you again will write a total and a net ionic equation. There will be a Canvas submission option, but I am going to, again, require you to take a photo of your work and upload it as the last question on the Canvas. So make sure that you do that. So, yeah. So if you're in Weaver's period, he's got it in his Chapter 10 module. So his Canvas is going to look a little different than mine, but it's because we're different teachers. All right. Okay, so like I said, we have this lovely worksheet. Right, so much stuff on it. Okay, so there's a lot of things that you have to remember. If you look in the instructions, there is this one little sentence that says, if the reaction does not occur. There's only one kind of reaction that doesn't occur, and that is a single replacement reaction where the replacing element is less reactive. Okay, so remember for reactivities, okay, you're going to have to refer to this constant and reactivity series worksheet. That's fine. You can call someone a turd. So remember on this worksheet, right, we talked about how to tell if something is going to replace another element. So make sure on single replacement reactions, this is kind of a big asterisk, big star. On single replacement reactions, you check to see if the reactions actually happen. Okay, you'd still identify them as a single replacement, but you want to check to see if they actually happen. Okay. I wanted to do one of these, just one though. Which one should we do? Got 20 problems. Did anybody actually start this yet? Lauren says, do 20. Yeah, we can do the very last one. That's fine. I'm fine with that. So reminder, on Wednesday, we are going to do more, like the whole day will be spent working on the worksheet. So we'll be doing homework help the whole day. So I'm going to do this example as kind of a last thing. And then on Wednesday, we'll go through the stream. On the right and left one is directly more reactive, higher or lower. So remember on this worksheet, Cooper, right, on this reference sheet, if you're looking at metal elements, right, the ones that are the first elements in the compound, higher is stronger. So lithium is the most reactive metal. And then if you're looking at non-metals, lower is more reactive. So fluorine is the most reactive non-metal, right? Lithium, most reactive metal. Fluorine, most reactive non-metal, right? So I guess we could say that gold is the least reactive metal. And we could say, or at least on this chart, and we could say that where like sulfur is the least reactive non-metal, right? Most reactive fluorine, least reactive sulfur, most reactive lithium, least reactive gold. The taco toaster, that sounds fun. Okay, so this one is hydroiodic acid, HI, reacting with lead to acetate. Cooper says, wait, he's confused again. About the reactivities? Cooper wants to make sure that he distances himself from Drake. Yeah. So here, let me. I'm still gonna have class on Friday, Kate. I'm still gonna have class on Friday. So here, Cooper, it's easier to just look at an example. So let's find a single replacement reaction. So let's look at this one, for example. Okay, iron and copper, right? The iron is going to replace the copper, or will the iron replace the copper? In order for this reaction to happen, iron has to be more reactive than copper. So if we go look at our list, iron is a metal, right? So we want to look on the chart, we want to find both iron and copper, okay? So let's see, here's iron solid, right? And then we also need copper solid. So here's iron, here's copper. Because iron is higher up on the list, it is more reactive than copper. And so because iron is more reactive than copper, the iron will replace the copper. Does that work? Does that make sense? Why isn't hydrogen the least reactive nonmetal? Oh, I guess you're technically right on that. But no, well, yeah, hydrogen's weird because hydrogen's 0. So yeah, I guess hydrogen would be less reactive than sulfur-ish. Hydrogen doesn't really react like a nonmetal. Hydrogen reacts like a metal because hydrogen loses its electrons when it reacts. So hydrogen is weird because of a lot of reasons, but when it reacts, it actually reacts more like a metal than it does a nonmetal because it loses its electrons. Oh, today is 420. That's pretty funny. Yeah, and even then, because hydrogen's on the right hand side here, hydrogen's actually more, in this case, it's more likely to act as a metal than a non-metal. Like, where does it go? So, Jonathan, in this reaction, the products of this reaction would be, oh my gosh, Ellie, stop asking me to say live, laugh, love. Iron is going to replace the copper, and so the products are going to be copper solid and iron sulfate. Okay, anyway, back to the reaction we're working on, number 20. Okay, let's go through how we would do this one. Yeah, Weaver is very much not a live, laugh, love person. No, it turns into solid copper, Jonathan. It turns the copper gets left by itself. It's all alone. Solid copper. Cu solid. Oops, wrong button. There we go. All right, so let's look at the reaction. So we have Hi plus lead acetate, okay? So if we have a compound plus a compound, what kind of reaction is this going to be? Or not compound, what kind of reaction is this going to be? Thank you, Enya. Double replacement. Right? So it's going to be a double replacement because we have two compounds, Ellie. If we had an element in a compound, then it would be a single replacement. Okay? So a double replacement, right? So that means our hydrogen and our lead are going to swap. Okay? And so we're going to get lead combining with the iodine, and we're going to get hydrogen combining with the acetate, HCH3COO. Okay. Now, we need to make sure we have the formulas right and the phases right. Okay, so formulas. So the lead over here is a +2, right? Because acetate's a -1, the lead has to be a +2. In a double replacement reactions, the charges stay the same. The charges don't change. And so on the product side, the lead is going to still be a +2. Okay, so if we look at our periodic table, iodine, being a halogen, has a charge of -1. So if the lead's +2 and the iodine's -1, we need a 2 there to balance it out. So lead iodide. With the acetic acid, hydrogen's +1, acetate's -1, and so it's just HCH3CO. Okay, so our products are lead iodide and acetic acid. Now, with double replacement reactions, in order to predict the phases, we need to refer to our solubility rules. Ta-da! Right, so these are the notes we took Friday. Okay, our solubility rules. Now, if you remember, there was something weird about lead. Okay, lead is solid with everything except nitrate. And so this lead iodide, if we were to predict the phase, we would say that it's most likely going to be a precipitate. Okay, so our lead iodide is going to be a solid because lead, if we're predicting, lead is insoluble with everything except nitrate. Now it turns out that lead acetate is a little bit soluble, which is why this is aqueous over here. But that's given to you. You don't have to worry about that. You're just predicting lead iodide, which is very much insoluble. Lead iodide is actually really pretty. I wonder if I could show you guys this reaction. Yeah, I'm going to show you guys a very similar reaction.
I died. As a test.
Whoa. That was not even that good. Blah. I wonder if there's a better one. Yeah, so what'll happen eventually is this yellow, it's forming this yellow solid, this lead iodide. So this yellow solid will sink to the bottom. There's a reason they used to use lead so much in paint, is because it makes really pretty colors. It's just toxic, right? Okay, so lead iodide solid. Acetic acid being an acid is most likely to be aqueous. Yeah, minor setback for the paint people. It's fine. Yeah, there are there are some really pretty pictures of lead iodide that's a little more golden looking. Those ones are really pretty. Okay. For sure. That always reminds me of the radioactive, the people that painted the watch hands, the radium on the watch hands that all got cancer because radium was radioactive. Because they used to make watches that had radium dials on them so they would glow in the dark. And the ladies that worked in the factories would paint them and they would lick them and they would get they all got radiation poisoning, which is crazy. Anyway, okay, let's see. Balance the reaction. We need 2 of these and 2 of those. Okay. Yeah, radium girls. Yeah, no, you're totally right, Johnny. I think that's what it was. Oh, there you go, Johnny. All right. So hydroiodic acid. When we go to a total ionic, does hydroiodic acid split? And why? Yes, says Hannah, it does split. Because it's a strong acid. That's not ionic, it's a strong acid. Okay. Now lead acetate splits because it's aqueous ionic chloride. So this is going to split into lead 2 plus and 2 acetates. Okay. Lead iodide is going to stay together because it's a solid. And acetic acid, does acetic acid split? So no, Hannah, it's not one of our strong acids, and so acetic acid's going to stay together. And so what are my spectators in this equation? What are my spectators? There are none. So in this case, there are no spectator ions, right? It's not the acetate because over here it's acetate and over here it's acetic acid. This does not split because it's a weak acid. So there are no spectator ions. And so if we were to rewrite the total ionic, it would, or sorry, the net ionic, it would be the same as the total ionic, right? So our net ionic is going to be the same. So there are sometimes cases where there are no spectators, and this happens to be one of those cases. Okay, so a few things recap. We knew it was double replacement because we had 2 compounds mixing together. We knew the lead iodide was solid because of our solubility rules. Okay, acetic acid, weak acid, right? This splits because it's a strong acid. There's a lot of things you just have to have memorized. There's a lot of things you just have to know and check yourself on, which is why this can be a little frustrating, is because there's so much stuff you have to keep straight. So hopefully you guys can be good on that. So I would just say, like, I'm going to be lazy and say same as above. Oh, did my wife is gone. I was going to ask if she was going to bring the kids up, but they're gone. Which is net and which is total. So again, this is total. All right. So the total ionic lists all of the ions involved. The net ionic has the spectators removed. Okay, and that's it. That's all I wanted to go through today. So recap, right? We talked about the decomposition reactions. So we talked about, in a simplest case, a decomposition is just a compound breaking down into its elements. And so we have these two examples of compounds breaking down into their elements, making sure that if you have a diatomic element, it is diatomic. And then we talked about three special cases: metal hydroxide, metal carbonates, metal bicarbonates, that break down as follows: metal hydroxide into the metal oxide and water, metal carbonate into the metal oxide and carbon dioxide, and metal bicarbonate into the metal oxide, water, and carbon dioxide. Okay, so that's kind of the day. So reminder, you've got this worksheet due. This worksheet is going to be due on Thursday night. I'm going to be working on the submission options for Canvas, but do expect that you'll have to upload a picture of your work as well. So make sure that you either print this off or just do it on a separate sheet of paper, kind of like I've done here, right? So kind of like I've done here, you can just use it on your own paper, but you do need to have work shown for every problem in order to get full points for the assignment. I'm going to be putting in the assignment from last week today. I'll be putting those into Skyward. So if you don't have them done, it'll show. Okay, you guys are all talking about paintings randomly. Yeah. That's kind of it for today. Have a great week. We should be getting information about like parent-teacher conferences at some point. We'll see what happens with that. But yeah. Shoot. I forgot to record this, so now I have to download the Twitch stream. Oh well. YouTube video might be a little late getting up, but that's okay. Yeah, definitely study your notes, says Weaver. Definitely study your notes, or at least have your notes organized in a point that you can reference them really easily. You want to be able to reference those notes pretty easily. Otherwise, you're going to be in a rough spot. Okay. Have a great rest of the day. Goodbye. Yeah, the test will be open notes, Sadie. So we'll talk more about the test on Friday. Goodbye.